So let me do this example. So this is our example. So the one is example 2. We will look at example number 3. Okay, now we're gonna do this example now. Okay, so this is statically indeterminate. Okay, so again we use our boundary condition. Okay, we apply our boundary condition. So we don't know what is our reaction. So at x is equal to 0, we don't know what is our shear force. We know the moment will be at maximum. Theta we don't know. So theta equal to 0, y is equal to 0, and the other side we know nothing. Okay. So we can start using the integration method now. Okay. So we have 1, 2, 3, 4 unknowns. Okay. So we have sorry we have more than 4. We have okay. So let's wait. Let's draw the free body diagram first. Okay, let's draw the free body diagram first. Okay, so free body diagram. So what is the question going to find is we're going to find the reaction. Okay, we're going to find the reaction at point B. Okay, now knowing that the structure is what? Statically indeterminate. Okay, we know that the structure is statically indeterminate, right? Because we can only form two. So the unknowns. Let's why is it statically indeterminate? Okay, so let's form the free body diagram first. Okay. So if we form the free body diagram, right? We know that we have a AY down here. We understand that we have a BY, right? And then we have a load coming down here. And this load is equal to omega naught L divided by 2. And the distance from here to here is L over 3, right? So we have a moment at point A. Okay, so if I draw this transformation, so this is X, this Y, this is rotation about Z. So we know that we have 3 unknowns. Okay, we know that we have 3 unknowns. Right, 3 unknowns. And using static analysis, okay, we use static analysis. Right, if we use static analysis, we can only find only 2 equations can be formed. Right? So just to recap, so therefore structure is statically indeterminate. Okay, right? So you cannot solve three unknowns with two equations. I'm going to, the reason why I'm doing this is I'm going to draw a center line. So I can do the whole example on one whole page. I don't need to change pages. Okay. So we can form the equation. Okay, let's form the equation and see what will happen. Okay, so let's use static analysis. So what we want to find is we're going to find by. Okay, we're going to find by. So we can do summation of forces in the y direction. Right? So we will have AY plus by BY minus by omega naught L over 2. Right? And then the whole thing is equal to 0. So we know that by is what we want to find out is equal to omega naught L over 2 minus by AY. Right? So by, yep. Okay, so this is our equation number 1. Right? So one equation, two unknowns we can't solve. Right? So we can take moment about point A. I mentioned about moment in the Z direction at point A. Okay, so we're going to take moment at point A now. So this will be equal to omega naught L over 2. So it's going in a clockwise direction. So we have omega naught L over 2 multiplied by 2L over 3 plus by by L. Right, the whole thing is equal to and then you have plus by M A. Okay, because now we're taking moment at this point over there. The point that I just drew the dot. So over here now we form equation. We know that moment at point A is equal to omega, or is equal to, or again, if we want to, I will write moment about point A. Now will be equal to minus or plus by omega naught L squared over 6. No, over 3, over 6, because you can cancel, right? Minus plus, so minus by BYL. Right? So from equation 1 and 2, we know that we can solve it. Okay, we have two equations, 3 unknown. Okay, so what we are going to do now, okay, what we are going to do now is we are going to form the moment equation. Okay, so remember this whole thing over here, we can start anywhere. Okay, let me elaborate what do I mean we can start. We are not going to start from dv over dx is equal to minus omega x. Okay, because we can start forming the equation. Okay, so we can start forming the equation. So we are going to start from m moment as a function of x. Okay, we're going to start from moment as a function of x. So what do I mean by that? Okay, so now going back to our free body diagram. Okay, going back to our for free body diagram. All right. So we know that over here, so this is from 0, and so on. So from A to B, from point A to point B. Okay, so the limit is 0x to L, right? So because we have formed the equation already, why not we use it? Okay. So over here, our AY, right? So if I look down here, our AY, so AY, I just rearrange the equation, right? So omega naught L over 2 minus by BY, right? And then our moment over here, right, is equal to omega naught L squared over 3 minus by BYL. Okay. Then because this is a function of X now, so the equivalent load, right, the equivalent load is equal to, so to find the equivalent load, let me do some side work. Okay, so we know that over here, this is X, this is omega, and this is omega naught, right? And this is L. The equation of the line is omega as a function of X is equal to omega naught over L X. Okay, so the omega equivalent is equal to omega naught X squared over 2L. Okay, so this is equal to omega naught X squared over 2L. And the distance from here to here is L or X over 3. Okay, so I'm going to take my moment at a certain distance X. Okay, so this will be equal to summation about moment in the Z direction. Okay, anyway, point X is equal to 0. So you have the first term is equal to omega naught L squared over 3 minus by BYL. Okay, then you have minus omega naught L over 2 minus by BY multiplied by X, right? Then plus omega naught X squared over 2L multiplied by X over 3. And we're going to assume positive shear, positive bending moment. Okay, then at that point you have plus by M as a function of X. The whole thing will be equal to 0. Okay, so now we are going to take out everything, right? So M as a function of X, this is equal to omega naught X cubed. Okay, omega naught X cubed over 6L. So positive you bring over will be negative, right? So in terms of X, you have minus, bring over will be plus omega naught L over 2X. Minus minus, take out is plus, you bring over is minus BYX, right? Then minus omega naught L squared over 3, and then plus BYL, and then this whole thing is equal to EI d squared y over dx squared. Okay, so this is where we apply. You can see down here we start applying the elastic curve already. Now, why I do this? Okay, I mean you can start like the previous example. Okay, you can start by forming the equation. You end up the same point. Why I did this is because over here we have three boundary conditions. 1, 2, 3. Okay, before that we only have one boundary condition over here, right? So I have three boundary condition over there, right? I can start forming from moment, right? We started from moment, right? And we also use the reaction at point A's, okay, to form the moment equation. Okay. So from here, we just need to integrate 2 times, right? So this is, I'm going to call equation 3A. So I'm going to copy, right? So I'm going to write up here. From here, it's all math, okay? Nothing to do with physics already. The physics part is done. So now we are going to put in EI dy by dx. We're going to integrate. So this is EI theta. So this is equal to minus omega naught x4 over 24L plus by omega naught L x squared over 4 minus by by x squared over 2 minus by omega naught L squared over 3x plus by by Lx plus by C1. Okay, so this is our